Welcome back, everyone. Let's get right into exactly what you need to absolutely master your data analysis for assignment 2. I know firsthand that crossing that bridge from just collecting data to actually analyzing it can feel incredibly daunting. But today, we're going to clear up all that confusion and give you the exact framework you need to succeed. Right now, you are probably staring at a mountain of questionnaire data, wondering what on earth to do next to answer your research questions. You've got your Likert scales, your demographic data, your test scores, but how do you actually extract meaningful, scientifically backed conclusions from all of that? And more importantly, how do you prove to us that your findings aren't just a total fluke? Well, here's our roadmap for today. We're covering 1. The why of statistics. 2. 3 core statistical concepts. 3. The statistical cheat code. 4. Building research hypotheses. And 5. The classic Pearson versus Spearman debate. Okay, kicking things off with Section 1, the why of statistics, moving from your sample to the overall population. Think of inferential statistics like a bridge. It allows us to confidently make big claims about a massive population based entirely on a much smaller, manageable sample. Obviously, you can't survey every single ESL student in Malaysia, right? That's your population. So you survey a sample of them. Inferential statistics, and specifically looking for statistical significance, is what lets you proudly say, hey, my results reflect a real-world reality, not just random chance. Moving right along to Section 2 are 3 core statistical concepts: association, relationship, and difference. Listen closely, because mixing these concepts up is literally the #1 mistake I see in master's research reports. There is a very sharp distinction between categorical association and the continuous movement of relationships. Association is strictly for categories. It's like linking male or female students to platforms like Duolingo or quizzes. But a relationship looks at how 2 variables move together. For example, as a student's confidence goes up, does their perceived user-friendliness of an SPSS workshop also go up? That is a relationship. And finally, we have difference. You'll use this one anytime you're pitting 2 groups against each other. If your research asks whether male students have higher confidence levels than female students, you aren't looking for an association or relationship anymore. You're looking for a clear, measurable difference between those distinct groups. All right, Section 3. This is the big one, the statistical cheat code, matching your variables to the right test. I highly recommend taking a screenshot of this slide right now. The crucial rule here, your mantra, is variable plus variable equals your test. This is the master key for your entire methodology. Got 2 nominal or categorical variables? You're looking for an association, so you run chi-square. 2 ordinal variables? That's a relationship, so you use the Spearman correlation. 2 interval or ratio variables? Also a relationship, but you use Pearson correlation. And if you have an ordinal variable being tested across 2 nominal groups, like confidence levels between genders, you're looking for a difference, so you use the Mann-Whitney U test. As you can see, choosing the correct test really isn't guesswork. It strictly depends on identifying your variables, whether they're nominal, ordinal, or interval. If you internalize this cheat code, you will never, ever struggle to justify your statistical choices to your examiners. Next up, Section 4, building research hypotheses, taking it from a question to an objective. This is where we take your initial curiosity and transform it into the strict 4-step structure that examiners demand in every methodology chapter. You start with the broad research question, turn that into a targeted research objective, and then split it into 2 testable hypotheses: the null hypothesis, which claims absolutely nothing is happening, and the alternative hypothesis, which claims something definitely is happening. Let's look at how this plays out with a TSL example about Duolingo and quizzes. Notice how the language is almost perfectly identical across all 4 steps, except for a few key action words. The null hypothesis, H0, stubbornly states there is no significant association. The alternative hypothesis, H1, states there is a significant association. Ultimately, your statistical test is going to tell you which one to accept. And that brings us to Section 5, the ultimate showdown for master's students, Pearson versus Spearman. You absolutely have to justify your choice here. You use the parametric Pearson correlation for normally distributed continuous scores, things with a linear relationship, like Mewit reading and writing test results. But you use the non-parametric Spearman correlation for your ordinal, non-normal Likert scale data. Think about it. Questionnaires measuring confidence or user-friendliness from strongly disagree to strongly agree are ordinal.
They're ranked, and they frequently violate the assumptions of normality, so Spearman is your go-to non-parametric alternative. Now, because Likert items are ordinal, you cannot just jump straight to testing. You have to prep your data first. First, reverse code any negative questions. Then, check your reliability. Your Cronbach's alpha needs to be 0.70 or higher. Next, compute composite scores for your constructs. But here's the trick. Use the median, not the mean. Why the median? Because again, your data is ordinal and non-parametric. Finally, run a Shapiro-Wilk normality test on those composite scores to officially prove to your examiners that the data is indeed non-normal and requires that Spearman test.
Okay, so you run Spearman and SPSS. What are you actually looking at? Well, you want the correlation coefficient and the significance level. In this output, looking at aggregated confidence and user-friendliness, we see a correlation coefficient, or rho, of 0.875, which we'd round to 0.88. And right below that, the significance, the p-value, is 0.000. Since that is less than 0.05, boom, we have a statistically significant result. And here is exactly how you report those findings in flawless APA style. You're showing a statistically significant, very strong positive relationship. You tell the reader exactly what test you ran, the variables involved, the direction and strength of the correlation, and you provide the exact rho and p-values. This right here, this is textbook perfection for your report. But what if you were looking for a difference between two groups instead, like male versus female students? Then you'd rely on the Mann-Whitney U test. Remember our cheat code? Ordinal variable plus a nominal variable with two groups means Mann-Whitney U. SPSS breaks down the groups and gives you a test statistics table right at the bottom. To report your Mann-Whitney findings correctly, you need to extract 4 specific things: the U-value, the Z-value, the P-value, and the mean ranks. So, from our previous output, we can report a significant difference because our p-value of 0.019 is less than 0.05. Plus, by checking out the mean ranks, we can confidently declare that female students with a mean rank of 38.11 reported higher confidence than male students who sat at 28.34. So, are you ready to tackle assignment 2? Take a hard look at your own variables, apply the cheat code rules we went over today, and you are going to absolutely nail the statistical analysis for your research report. Let this framework guide you, and inferential statistics won't be an obstacle anymore. It'll be your most powerful tool. As you open up your own datasets today, ask yourself, what hidden truths are buried in your students' responses right now, just waiting for the right statistical key to unlock them? Good luck, everyone.